Assalamu alaikum. Welcome to another episode of Operating Systems. In this particular lecture, we're going to extend the scheduling introduction that we started in the last lecture. Now, this particular lecture, in the last lecture, we made specific assumptions. And one of these specific assumptions, and those assumptions were basically, all jobs are arriving pretty much at the same amount of time, once started, each job runs to completion. And one of the critical was the runtime of each job is known. And now, obviously, during the course of the last lecture, we relaxed each of those assumptions. But one assumption we did not relax was the runtime of each job is known. So in this particular lecture, we introduce a framework which is called multi-level feedback queue. It won a Turing Award. And the aim is, first of all, we don't know anything about a process. So the assumption, we're relaxing that as well now. We don't know anything about the process. So how can we build a scheduler to achieve this? So the first priority is to optimize the turnaround time, a metric that we introduced in the last episode. The turnaround time is the time it takes between the time when a process arrives and the time the process completes. This is the turnaround time for a job. A job is another word for process, which is another word for, let's say, program. Now, at the same time, uh, response time is how much time it takes for the CPU to run a process the first time it came. That is the response time. And we want to minimize the response time without prior knowledge of the job length. So our initial assumption, we've relaxed that. In general, we don't know anything about a process. So how can we build a scheduler to achieve those goals? Now, multi-level feedback queue, MLFQ, the fundamental element helps doing that. And the MLFQ has fundamentally several queues, as the name suggests. There are multiple levels of queues. And a job which has on a higher queue has higher priority as opposed to a job at a lower queue. Now, within the same queue, jobs run in round robin fashion. So here, rule number one of MLFQ is if the priority of a job is higher than the priority of another job, then the one which has higher priority runs. But if both of them have the same priority, then A and B both run in round robin fashion. Now, as an example, what about how does the MLFQ behave if but there is a feedback process, it's a multi-level feedback queue. So we understand about the multi-level queues. For instance, here is a multi-level queue. You can see there are about 8 queues shown here, where Q1 would be the lowest priority and Q8 would be of the highest priority. In this particular instance, if you look at rule 1, A and B have higher priority than C and D. So an A and B run. But what happened? But within A and B, because they both have the same priority, then they run in round robin fashion. But the fundamental is how do we introduce a feedback? The feedback is done by observing the behavior of the process. If the process is, let's say, allocated hypothetically 10 or let's say 100 clock cycles of the CPU, and the job itself relinquishes the CPU after 80 clock cycles. It doesn't consume the entire time period or the time slice. It doesn't consume the entire time slice, but rather relinquishes the CPU. Maybe it has to do some input output. Maybe it has to do something else, but it relinquishes the CPU, says, you go ahead. Why don't you do something else? and you take over, actually, the operating system. Why don't you take over and help me with this task? In that case, because it exercised good behavior, the OS will retain it within its priority level. But if a job says, I am going to use all the time allocated to me, this is fair, I was allocated 100 time cycles, I'm going to use 100 time cycles, or I was allocated 100 milliseconds and I'm going to use all of 100 milliseconds, then the OS will say, this guy is very aggressive. I'm just going to lower it priority, and I'm going to allow more nicer processes, more well-behaved processes to continue. I'm going to give them higher priority. So that is how the feedback is integrated within the framework. So let's look at this. So when a job enters any system, it is placed at the highest priority. It makes no assumptions because we don't have prior knowledge about the job. We don't have prior knowledge about the process. So every job, when it enters the system, is given the highest priority. If the job consumes its entire time slice, then it wasn't very well behaved. Then, I'm going to reduce the priority of this job during the next iteration. Okay. But if a job relinquishes the CPU and says before the time slice is up, it retains the same priority. What does that mean? Let's look at this job. A job, let's say A, comes, it's given in this particular multi-level feedback queue, there are just 3 levels. So the highest level being Q2, the lowest priority being Q0. So when a job comes, it's given the highest priority, it's at here. After one time slice, because it consumes the entire time slice, in the next time slice, it's placed at a lower priority level, Q1. And thereafter, if it consumes the entire time slice, it's put into the lowest priority level, or the priority level 1 below it. Here, the lowest priority level is Q0. Therefore, once it comes at Q0, it stays at Q0. Okay. That's how the feedback mechanism is introduced. But let's look at another example. Okay. In this particular instance, now once a particular job A is already placed in the lowest priority level, maybe it is a CPU intensive job, it consumes the entire time slice whenever it's allocated the CPU. And then comes along another job, let's say, which is a shorter interactive job. What you see here is that once this job arrives at this particular time instance, because when a job comes, it's placed at the highest priority level. So at this particular instance, there are 2 jobs in the system. The first is B, which is at a higher priority level, and the second is A. So from 0 to 100, there was only one job, which was A, and therefore it ran. But once at timestamp 100, or at the 100th millisecond, another job came. Because when a new job comes, it's placed at the highest priority, B has more priority than A, so B runs in the first time slice. Once the time slice is over, because B consumed its entire time slice, B is placed at a lower priority level, Q1. And now at this times int stamp, there are again 2 jobs, B and A, but because B is at Q1, a higher priority level than A, B runs first, it completes its task, and then A continues. Right? So this is one way how smaller jobs or newer jobs have excellent response times, because as soon as they came, they were placed at the highest priority level, and therefore they were given the due time that they needed. Now, Let's take another example. In this particular instance, you have A, which has been there running for a long time. It's a long running CPU intensive job. In other words, whenever A is given the CPU, it consumes the entire time slice, maybe because it's doing some important calculations. Whereas B is an interactive job. Maybe you're using the controller or you're using the mouse or you're using the keyboard. And, so whenever B arrives, B is placed at the highest priority level. Now, because you can see here the length of the time slice, it's actually thicker, whereas B doesn't consume the entire time slice. Before the completion of the time slice, it hands over the CPU back to the operating system, maybe because it goes into a block state, maybe because it needs to interact with something, maybe it needs to do some input-output operations. Now, because B is behaving very politely and it's relinquishing the CPU in every time slice, B retains the highest priority. Okay. Now, when B retains the highest, this is how it's moving on. Okay. Now, so an interactive job is being always placed at the highest priority. Now, you can see here, now, at this particular time instance, now you could say, well, you know what? There was B here, and then there was A. B had a higher priority than A. Why did A run? Well, the only reason A is, even though B has a higher priority, the only reason A is running is because B is likely blocked. It's not in a ready state, it's in a block state, waiting for some input output that it had to do. Now, as soon as the input output is done, it goes from maybe during this time, it was handling its input output. And when that was done, it goes back from the block state to the ready state. So in the next time slice, B runs again, because in this moment, there are two jobs which are in the ready state. One is B and one is A. B has a higher priority. B runs. A doesn't have a higher priority, so A does not run. And then before the time slice, B again relinquishes the CPU. Now B is no longer in the ready state. B is in the block state because B is waiting for some input output. Now, because B is waiting for some input output, the only job which is in the ready state is A. Therefore, A runs. And that's why you see it, the CPU flickering between A and B, switching between A and B. Okay. Now, so think about it. If there were too many interactive jobs in the system, or if there were too many jobs at the highest priority level, how can the little guy do work? How can jobs which have lower priority level ever get done? They will never receive any CPU time, right? More like a government, imagine a government office receiving high priority work all the time. What will the little jobs have? When will the little jobs get done? Well, they never get done by that notion. So, how does one help in the starvation? It's called starvation because the lower priority jobs are starved. They're waiting for the CPU. They're never given in a CPU in this particular instance. How can we resolve that? The other problem is some jobs, some viruses even, might actually try to game the scheduler. That is, after running 99% of the time slice, it suddenly issues an input-output operation. Think about it. If you have a job that is allocated 100 clock cycles, the job actually consumes 98 clock cycles, and in the 99th clock cycles, it issues an input-output operation. Well, it's effectively using the whole time slice. So how can we resolve something if a particular job, it may even be a it's seemingly is a CPU intensive job, it's masking itself to be a very nice guy. It's the job is staying at a higher priority level, it should come down. Okay. And a program may also change its behavior over time. It was initial. How can let's say it's a CPU bound process, it's really trickled down over the different time slices. It's trickled down from Q2 to Q1 to Q naught now. So it was a CPU bound process. Now it's completely Q naught. Well, if it's Q naught, it stays in Q naught. Now, if it changes its processes, behavior over time, and now it's an input-output bound process, it's actually relinquishing the CPU before every time slice finishes. So now, if a bad boy has showing good behavior, shouldn't we give them some encouragement? Not in this system right now. No, we need to do something. We need to make some changes so that as a bad boy, if you're showing good behavior, your priority level should be raised. How do we handle those things? Let's look at some examples here. Here, we see that a particular job came first. It was the only job. Whenever a job comes, it's given the highest priority. So it was at Q2. After the time slice, it ended up Q1. After another time slice, it seemingly consumed the entire time slice. It ended up at Q naught. Once it's at Q naught, it stays at Q naught. The reason it's running, it's because this is the only process in the CPU at that given time. But now at about 100 timestamp, there are two jobs which arrive. So there was a long running job A, and now there are two jobs that arrive pretty much at the same time, B and C. These are short interactive jobs. And they are short because you can see here that the time slice is larger in width and they're actually taking less time. So B, is that B and C both are given the highest priority. B works for a portion of the time slice, let's say 50%, it relinquishes the CPU. Wonderful, good behavior. I'm going to keep it at higher priority. And then C comes, consumes the time slice, maybe 50%, and then hands it over to the operating system, says, go ahead. I'm waiting for some input output. Wonderful, good behavior. It handed over the CPU before it finished, but it's going to stay at the higher priority. So then what you're doing, you're really flickering between B and C. And B and C, because they showed good behavior, they relinquish the CPU before the time slice ends, they're always at the higher priority. A never gets to do anything. A doesn't get anything done. So in this particular instance, A is facing starvation. Okay, more like the people of Gaza, let's all starve them, right? That's what the Israelis are doing, and the whole Muslim world is watching. Uh, all the Muslim armies are watching, exploring their feminine side, their touchy feels, and they're allowing the starvation to continue. Yeah. Uh, yeah, very brave of them to utter deep, concerning words. Very courageous of them. We can all see, right? But anyhow, this is, then in this particular time, in this particular framework, these low priority jobs, they never get the time of the CPU. So now what you do, you issue what is referred to as a priority boost. Now, the priority boost basically does what it does. It says, listen, I am going to allow uh, and this you need to do because some programs might actually be gaming the scheduler. They would be consuming or even 80% of the time slice and then say, hey, go ahead, take the CPU. CPU, we're all yours. I don't use all the time effectively. I'm going to actually be using it. So what do? You need to change the program. You need to update its priority after a particular time instance has occurred or after it has consumed X number of time slices in the lowest priority. You need to boost it back to the highest priority. So you're basically what you're doing is periodically boost the priority of all jobs in the system, not just A. I mean, here right now we only have A, but periodically boost the priority of all jobs in the system. So what you're doing is after some time period S, move all the jobs in the system to the topmost priority. So now you've moved it to the topmost priority. Here, you can see now, you see A, B, and C moving in round robin fashion because, A likely is also now behaving very well. It was a CPU intensive task here, but now it's an interactive task. So that's why over multiple time slices, it's actually uh, has the highest priority. Okay, wonderful. So now, what about how to prevent once a job uses, and how do you prevent gaming the scheduler? Now, this is called gaming tolerance. And what you do in the gaming tolerance is you can see here this job, right? It uses almost all the entire time slice, but it relinquishes the CPU at this point in the instance. So it seems that it's behaving well. So, you give it its due time. And obviously, at this time, it's waiting for some input output. So it goes from the running state to the blocked state. So at this particular time instance, it is only this job which is in the ready state, therefore it runs. And it runs for a brief little time period. And then you know what? An interrupt is given where Q2 is now this particular job is from the block state to the ready state. Now, because it's in the ready state, it just arrived in the ready queue. Because it has the higher priority, it again runs. And again, it uses, let's say, 90% of the time slice, and then it issues an input output request to the OS. It relinquishes the CPU, and now it goes to the block state. And at this time instance, the only thing which is running is this guy. It's in the ready state, so it runs. And then as soon as the input output is done, an interrupt is occurred telling the CPU, listen, this task is now a ready state because it's at a higher priority level, it runs again. So basically, B has almost complete monopoly over the CPU. A has to wait. Now, to avoid something like this, there's another rule which is introduced, which relights rule 4A and 4B. It says once a job uses its time allotment is at a given level, regardless of how many times it has given up the CPU, its priority reduces. So here, let's say there is a time slice, which is, let's say, 100 clock cycles. That's the time slice. It's the same for every process. But then there's another parameter called time allotment. And let's say that's 1000 clock cycles. So after a particular process consumes those 1000 clock cycles in the CPU, its priority level is reduced. Now, once its priority level is reduced, it will eventually come to the lowest priority level, and then processes at the lowest priority level run in round robin fashion. Hence, not only introducing tolerance, but more fairness in some sense, to allow all processes to get their fair share of time in the CPU. Now, another element is which is called lower priority, longer quanta. So processes at the higher priority level are given a larger time slice, but as they go down the priority level, their time slice increases or the quanta size increases. That way, processes which are CPU intensive, which you're doing some very meaningful calculations, do get the time they need to do those meaningful calculations. Okay, so that's how lower priority jobs also eventually get done. So what you have is basically, for instance, the Solaris MLFQ implementation has 60 queues, right? Where the highest priority quanta or the time slice length is 20 milliseconds, while as the lowest priority has a few hundred milliseconds. and priorities are boosted for every after every 1 second or so, and that's the Solaris MLFQ system. So, in summary, your multi-level feedback queue removes this first assumption that we know how the processes are going to behave and how long they're going to run. We don't know that. So how do we resolve this? Well, use multi-level queues, priority queues, and you put in a feedback process in there. The advantage of multi-level queues is, well, if a process has a higher priority than the other process, then A runs and B doesn't, assuming they're all in the ready state. Now, if priority A is the same as priority B, both run in round robin fashion. When a job comes, it enters the highest priority level. And once a job uses its time allotment at a given level, regardless of how many times it gave relinquish the CPU, its priority level is reduced. And obviously, after some time period S, move all the jobs to the topmost priority. There's another rule which it just kind of like missed, was that lower priorities. You can tune the MLFQ further so that lower priorities have larger quanta, as is done by the Solaris MLFQ's implementation. So Solaris MLFQ has a rule 6 as well, which is lower priority, higher quanta. Okay. So I hope that helps. See you inshallah ta'ala next time. Thank you very much. Have a good day. Bye bye.